Okay, so let me introduce you to ChronoZoom with Roland up here piloting our time machine. So first, we'll travel backward in history, with ChronoZoom giving us a graphic understanding of the vastness of time, and then we're going to return to the present with ChronoZoom in its research tool mode. Let's start at Millennium Eve on December 31st, 2000. There are many themes we could look at in human history, and hopefully someday ChronoZoom will have a large selection of them. But for today, in keeping with our topic of Earth history, we have chosen to look at the way in which human beings have come to understand our planet. Here is the second millennium that has recently ended. And here in blue are the episodes in geology that I personally have had the good fortune to be involved in. Now, zooming out, we can place them in the broader context of modern geology, seeing the plate tectonic revolution, Alfred Wegener's continental drift, and the 19th century geological revolution, from Hutton's discovery of deep time to Darwin's theory of evolution. Now we can see back as far as, in the Western tradition, there are studies of the Earth that we might consider scientific. Although I don't have time to go over them all in detail, you can look at them online tonight. Another zoom, and we've reached the limit of written human history about 5,000 years ago, symbolized here by ancient Egypt in the timeline across the bottom. There was not much scientific geology early on, but people made skillful use of Earth resources, building the pyramids, shaping Egyptian granite into obelisks. And if during this zoom you had been watching the New Year's Eve with which we started, you would have seen it shrink into less than 1 pixel in the upper right-hand corner of this image. This is the problem of timescales that makes it so hard for us human beings to comprehend all of human history. But we're just at the beginning of our difficulties if we want to understand the timescale of big history. Earth history goes back to 5,000 million years ago. Now, it may be helpful to know that Earth history is about 1 million times longer than human history, but that does not really convey a gut understanding of the chronology. We're finding that ChronoZoom can help our understanding, especially if you spend time playing around, zooming in and out and panning back and forth. So now, let us zoom slowly back in time. I will just point out when we pass the limits of prehistory, life history, and Earth history. So here we have zoomed out 1,000 times and reached the limit of human prehistory about 5 million years ago. Another factor of 1,000, and we're back to the formation of the Earth about 4.5 billion years ago. One last zoom by a factor of 3, and we can see all of cosmic history back to the origin of our universe and of time about 13.7 billion years ago. The origin of the universe in the Big Bang is understood by cosmologists back to the first 10 to the minus 43 seconds. Think about that. And the only practical way to show it is on a logarithmic plot, which we've done for the first billion years. So this is ChronoZoom in its time visualization mode. We hope you like it and that you will take some time to explore it online. And I really do want to thank Roland Saekow, along with Bill Crow, Goldie Jodary, Karan Singh, Melinda Minch, and Asta Roseway for bringing it to life. Now, let us return slowly to the present, thinking about how ChronoZoom might be useful as a research tool. We're only beginning to explore these possibilities, so I will be showing you ideas rather than results. Now, across the bottom, here, you see the divisions of geological time. And above that, the decay of various radioactive isotopes produced during the supernova that triggered the assembly of the sun and the planets. And at the top, the growth of the Earth. Here's its assembly, and of its iron core here in purple during the accretion of our planet. Panning across toward the younger times to the right, we come to the last 542 million years, which geologists call the Phanerozoic, or the time of abundant, visible fossil life. These are the times about which geologists know the most because of the rich fossil control. But now, with radiometric dating, our understanding of times earlier than 542 million years is rapidly increasing. For example, geologists are now working out the history of the supercontinent cycle, in which a landmass containing most or all of the continental crust breaks up into several modest-sized continents, which then break up and reassemble someplace else into a new supercontinent. As a result of this work, many hundreds of paleocontinental maps have been published. Like these for 560 and 540 million years ago. These were made by Ron Blakey at Northern Arizona, and there's so many and they're so complicated that they're very hard to keep track of and digest. With the zooming capability of the new tool here, we can display hundreds of these maps in chronological order so they can be studied and evaluated. In addition, we can build in new kinds of diagrams like this one that uses the concept of the biological cladogram to clarify the inferred history of supercontinent breakup and reassembly. For example, here is the gradual assembly from 700 to 500 million years ago of Gondwana in black. This is the supercontinent. Now the vertical red bars mark the collision of continental fragments like here, and the blue bars mark rifting events in which larger continental masses are broken up. And notice here how Goldie's team has placed a scale, a time scale, across the top, so you can always see where in time you are located. Panning toward the right, towards younger times, we see the collision of Gondwana here with Laurussia, which means North America plus Europe, that built the Appalachian Mountains right here, and assembled the full supercontinent of Pangaea, which then fragmented into the familiar continents of today, and that's what's happening over here. It was this fragmentation that Alfred Wegener correctly understood in the 1920s. ChronoZoom has been allowing us to compare and test the many possible histories that have been suggested. We can also look at the history of impacts. Here are all the major impacts back to 400 million years ago, with arrow length proportional to crater diameter. The 170-kilometer Chicxulub crater produced a mass extinction. The 100-kilometer craters at Manicouagan in Quebec, at Papagai in Siberia, and at Chesapeake Bay did not. And here is a most exciting new discovery. This is just a wonderful one, made by Birger Schmitz in Sweden. There was a huge storm of impacts that pummeled the Earth for 1 million years or so, after a collision broke up an asteroid between Mars and Jupiter. It happened during the Ordovician. Remember that? 488 to 444 million years ago. This was the time of the Saharan glaciation that so intrigued me when we lived in Libya. The Ordovician glaciation in the Sahara was a normal glaciation, but here are, a bit older, are two superglaciations, or snowball Earth events, in which the ocean's surface was frozen from one pole to another. ChronoZoom lets us plot together all these different kinds of historical information at different time scales. Normally, all of this information is presented separately in different diagrams, usually with the time axis running in different directions, and is really hard to make sense of. But I'm optimistic that bringing it all together in ChronoZoom will lead us to a new synthetic understanding of Earth history. Let's now turn briefly to the history of life. Because of its enormous complexity, let's just focus on the ancestry of human beings shown in the upper part of this diagram. And here is the beginning with Luca That's not an Italian guy, that's the last universal common ancestor. And branching into the single-celled archaea and the eubacteria. Now, panning towards younger times, we see the endosymbiotic event here that produced our eukaryotic cells, and the initial branchings that eventually led to us up here. In this drawing, the lineage ancestral to Homo sapiens is always at the top. You'll be able to follow it up there. The so-called outgroups that do not lead to us, like plants and fungi, are shown below, and we've left off their own complex pattern of branches. But here we encounter a major problem that could be studied with ChronoZoom. You can derive the history of life based either on fossils or on DNA. Now, the fossil-based paleontological record is very detailed and can be tied into the geological timescale, dated in millions of years. But it is not always easy to figure out the genealogical relationships, and the branching dates can be suspect, for the oldest members of a group may not be preserved in the fossil record. On the other hand, if you compare the DNA of various living organisms, the closer the match in DNA, the more closely related they are. But this approach has its own limitations. You can't get reliable DNA from extinct lineages, and there's no direct way to date the branching times. So perhaps not surprisingly, the two approaches do not give exactly the same tree of life. Now, the most troubling discrepancy that's really bothering people who are concerned with the history of life is in dating the branching times. The DNA tree, which is usually dated on the basis of the dubious assumption of constant mutation rate, commonly gives nodes substantially older than the fossil record does. Now, in this drawing of the family tree of humanity, I've used the DNA data, but only because there is a recent systematic compilation called the Time Tree of Life that gives a coherent, internally consistent evolutionary tree with assigned dates. We really need a similar compilation for the fossil-based tree, and then we need a rigorous comparison. ChronoZoom should help, as you will see as we trace the pathway on towards human beings. Here we see the eumetazoa, or the true multicellular animals, splitting off from sponges, and then dividing into animals with radial symmetry, like corals and jellyfish, and those with bilateral symmetry, like us. A few more branches, and we come to a major problem. The Cambrian explosion of multicellular life, which is a really important feature of the fossil record, is simply not apparent from the DNA evidence. Nobody knows what the answer to that is right now. Now, tracing our chordate and vertebrate ancestors, we come to a branch or a clade called the Gnathostomata here, or jaw-mouthed animals. And here you see the problem of dating, for this DNA-based tree places the origin of the jaw at about 600 million years. You can see there 0.6 billion up there. Whereas the fossil record is quite clear that the jaw appears, guess when? In the Ordovician, maybe 460 million years ago, when Birger-Schmitz's asteroid shower was falling and glaciers covered the central Sahara. A few more branches, and mammals split off from the reptiles. More and more mammals split off, and our lineage continues into the primates. We continue through old world monkeys and apes and hominids, and then to humans and our extinct relatives. Now, in a moment, we're going to look more closely at human prehistory, but first let's zoom quickly out to see the entire history of life and Earth, and then back in once more to place humanity in our big history context. Okay, now let's have a closer look at prehistory, human prehistory. Here at 4.4 million years ago is Ardipithecus ramidus, described last fall by Berkeley's Tim White and many colleagues. And a bit younger, at 3.2 million years, is Australopithecus afarensis, the famous Lucy. Continuing to younger times, we see other Australopithecines and the various species of genus Homo, leading to our own species, which is the only hominid which is still alive at the present time. Now, across the bottom, you can see the geological time scale, the geomagnetic polarity sequence, and the oxygen isotope record of glaciations from the present back to a bit more than 5.5 million years ago. The orange box over here indicates a remarkable event in Earth history, the MSC, or Messinian Salinity Crisis, in which tectonic uplift blocked the passage between the Atlantic and the Mediterranean, and the Mediterranean simply dried up by evaporation, turning into a desert about 2 kilometers below sea level, and about the size of the United States. It was this evaporation that left a thick layer of salt on the floor of the Mediterranean, all except for the southeastern corner of the Tyrrhenian Sea, which opened after the salinity crisis, as my Italian colleagues and I predicted in the 1970s. Now, an event like the salinity crisis would obviously have many geological consequences. Let's just focus on one, the evolution of the Nile River. When the level of the Mediterranean Sea dropped by 2 kilometers, the Nile was able to erode down to that level and also to erode far back upstream to the south. And this, of course, led to the origin of this Grand Canyon-sized filled-in chasm below Cairo and of the smaller buried valley beneath Aswan. I realize that I'm running a little longer on this than I wanted to. Shall I go through it all, or shall I jump ahead? Continue? Okay, all right, I will. Thank you. Okay, so the Egyptian geologist Rushdie Said was the first to formulate a coherent theory of the Nile. The Nile is the most fascinating river. He based it on sediments along the Nile Valley. He recognized several different phases in which the river either deposited sediment or eroded away. But it was really hard to date these different phases because when you get back beyond 50,000 years ago, the limit of radiocarbon dating, there was no way to obtain ages directly. Now, Said's preferred chronology is shown in blue, while other geologists have suggested slightly different histories shown in pink and green. And Eo-Nile is the name that Said gave to the river that eroded the Great Canyon when sea level was low in the Mediterranean. Now, that river, of course, just simply ceased to exist when the Atlantic broke into the Mediterranean desert and suddenly filled it up, and filled up that long canyon going all the way back up to Aswan. As the elongate gulf filled with sediment, a new river, the Paleo-Nile, gradually extended its mouth downstream. Our different geologists have different ideas about just when this happened. You can see here and here. We then enter a complicated interval in which sometimes there was a Nile fed by abundant rains farther south in Africa, and sometimes the Nile did not reach the Mediterranean at all. It just simply evaporated before it got there. As you can see, there's no agreement about the timing or even the nature of these phases, and my point is to show you how ChronoZoom might help resolve this ambiguity. Drill cores, this is a set of drill cores from the eastern Mediterranean, bring up white sediment interrupted by dark organic-rich layers called sapropels, these ones in here. Sapropels are thought to represent time when the sea bottom was oxygen-starved, so that scavengers could not live there and eat the organic matter that fell. Oxygen starvation was probably due to a layer of fresh water from the Nile that floated out over the sea surface of the Mediterranean, inhibiting overturn so that oxygen could not reach the bottom. So here you can see a sediment core cut into several segments with several numbered sapropels, 68, 70, 75, and so forth. And further to the right, you can see ages that have been assigned to some of these sapropels on the basis of the Earth's orbital Milankovitch rhythms, which provide a kind of clock. Now, you can see that the sediment record along the Nile Valley indicates a time when the river stopped flowing in here, different times for these different people. It's been hard to date. Meanwhile, there's an interval up here in which sapropels did not form, and this may well be the record in marine sediments of the arid phase during which the Nile did not reach the Mediterranean and spread fresh water out all over it. So maybe this will turn out, and the questions there, question marks, maybe this will turn out to be a new way to date the history of the Nile. ChronoZoom encourages us to plot together data sets like these, which are rarely combined, and this may lead to improved chronologies and in turn to a fuller and better understanding of Earth history. And of course, we can understand all this Earth history as the foundation on which human history has been built, from the old kingdom of Egypt to the growing scientific understanding of Earth history to the times we live in today. So this is ChronoZoom. I hope you will explore it online, and if you have comments or suggestions, or if you would like to get involved in turning this pilot version into a fully operational tool for big history, please get in touch with Roland or me. There's contact information on the website. I had some other neat stuff I was going to tell you, but it's just gotten late. I think I better stop and urge you, if you have any interest in this, get in contact with us. If you'd like to get involved in turning ChronoZoom into a tool that would help you with your interest in human history or life history or cosmic history, we're just hoping we'll find some people who would like to do that. Thank you so much for coming today. Thank you, Chancellor.